Hi y'all, welcome back. So in the previous video, we finally derived the complete places equations. But the most important thing is after deriving an equation, we learn how to use it to apply it, and that's what makes us an engineering majors. So now let's stay tuned and follow me to tackle problem 2. So all right, problem 2. So what does problem 2 ask? Problem 2, we have how many part? We have 4 part A to D. So the first part, they say given that Vx over Vx infinity equal to 2 times y over delta minus y over delta square. They ask us to derive delta over x as a function of Reynolds number with respect to x. Okay, and what is Reynolds number with respect to x? Reynolds number with respect to x equal to rho times u infinity times x over mu. Okay, so the problem asks us to find this expression right here, okay, as a function of this expression right here, and that the Reynolds number is equal to this expression. Okay, so you notice that Vx over Vx infinity, this is one way you can fit the equations, right? You notice how all these terms right here on my top left is been written in dimensionless form. So Vx over Vx infinity, the velocity unit cancel out, y over delta, the length unit cancel out. So all this is written in dimensionless number. This is one of the curve fitting technique, which is very widely used. And today we'll use the equation to actually derive delta as a function of x and Reynolds x Rex. Okay, so let me write some notes here. So usually with this type of question, you will use the integral to solve for delta. Then you will do necessary manipulation. So I will break down this problem into 3 steps. The first, you use the integration, then you solve for the profile, and then you integrate. You take the derivative. I'm sorry. So what equation will we use? So, right, what equation are we using? Okay, well, the equation we're using is equation 8.4 we just derived. So let me rewrite for y'all that one. So equation 8.4, what does it say? It say, I'll write in blue, okay, Vx infinity times d over dx of integral from 0 to delta of Vx dy equal to integral from equal to d over dx of integral from 0 to delta of Vx squared dy plus tau w, oh my bad, tau w over rho. Okay, this is the equation we use, equation 8.4, the Laplace's equation. Okay, now we have the equation down, we have the goal, delta over x as a function of Reynolds number. Let's go ahead and get started. Okay, so this problem has been breaking down to multiple steps. Okay, so let me write that for you. So step one, evaluate two integral. Okay, evaluate the two integral. What is those two integral? This integral right here is the one we will evaluate. Okay, and then we take the derivative and we use some separation variable techniques and we will obtain the profile. That is the general general scheme to do these problems. Okay, Vx depend, right? So then this problem, they give us Vx equal to Vx over Vx infinity equal to this. So we can do some manipulation and we can get Vx, okay? Okay, I'll evaluate the integral. So let's call our first integral with a name, label it with a name, I1, okay? So what's I1 equal to? Our I1 right here is 0 to delta of Vx dy. Notice that the problem doesn't give us Vx, they give us Vx over Vx infinity. So we have to make Vx infinity appear. So the trick is you just equal to 0 to delta of Vx over Vx infinity times Vx infinity times dy. Okay. Notice Vx infinity is a constant. So you can put it out. So it's Vx infinity times integral from 0 to delta of Vx over Vx infinity times dy. And then now you can substitute in the equation above. Let me call it 1. This is equation 1. So you can substitute in 1. You get is equal to Vx infinity times integral 0 to delta of 2 times y over delta minus y over delta square on of this dy. Okay, let me highlight this so y'all make sure what term substitute in. Okay, let's go ahead and evaluate this integral together. Wolfram Mathematica can definitely do this, but I'll show y'all how to do it by hand. Keep in mind that y, this is dy, right? So we have this is dy. So y is a variables and the rest is a constant. So let's organize our integral a little bit nicer so that we know. Okay, so I rewrite so Vx infinity times integral from 0 to delta of 2 over delta times y minus 1 over delta square times y square on this dy. Okay, y'all notice that how I separate the y and it's constant on one side. So 2 over delta is a constant, 1 over y squared is a constant. So now we can do the integral. So Vx infinity integral from 0 to delta of 2 over delta times y squared over 2 minus 1 over delta squared times y cubed over 3. Okay, y'all treat 2 over delta and 1 over delta squared as a constant, like 2, 3, 4, 5, anything. Okay, so let's clean it up a little bit. Vx infinity over from 0 to delta y squared over delta minus y cubed over 3 delta square. Now I can substitute in, so the variable, so equal to Vx infinity times delta square over delta minus delta cube over 3 delta square on this minus 0 square over delta minus 0 cube over 3 delta square. Okay, so all this becomes 0. Finally, you get Vx infinity times delta minus delta over 3. So you get Vx infinity times 2 over 3 delta. Beautiful, beautiful, beautiful. And ladies and gentlemen, that is your first integral.